Today's lesson is on the continental drift theory. Alfred Wegener was a German scientist. He was a geologist, and he noticed that rocks and fossils were found on continents that were actually separated, but the continents seemed to fit together like a puzzle if you would combine them. These similar rocks and fossils led him to believe that, hey, maybe these continents were once together formed one big massive supercontinent, and he called this Pangaea. So Alfred Wegener was the one that came up with the idea of Pangaea, the supercontinent. In 1912, Wegener published the first version of his book describing what he believed, and before it could ever be proven true, he died defending his theory. At that particular time when he was still living, other scientists thought he was a little crazy. They said, what proof do you have? Give us evidence. We need evidence. We're scientists. We need proof. And he said, well, the rocks and fossils are the same. He said it kind of looks like it fits together like a puzzle. And that was not enough for the other scientists to believe. They said, we need proof of what moved those massive pieces of land. And he didn't have any idea on that, or he didn't have an answer, so they just chose not to believe him. But he did die before he ever figured out that what his ideas were totally true. The supercontinent made up all the continents and joined together about 250 million years ago, and what he said was it kind of slowly broke apart, and over millions of years separated into the continents we have today. And the word Pangaea comes from the Greek language, meaning all land. Continental drift theory is stated that the Earth's continents have been joined together and have moved away from each other at different times in Earth's history. The picture on the top left is Pangaea. It's at 225 million years ago, and through time, this is how he said that they would have changed to look like the present day, what we have now. And if you look at it, it really does look like it could have been one piece of puzzle, doesn't it? Support for the continental drift theory. The first support was the shape of the continents. We've already said that, and you could see in the pictures that it looked like all the continents were once together, fit together like a piece of a puzzle. Alfred Wegener also came up with the maps that he drew and explaining his idea of continental drift. The second support was fossil evidence. The same fossils were found on different continents. So the fossils that were found on South America were also found on Africa. And it makes sense if those continents were slid together to form like a piece of a puzzle, that once they did split, that would be a good enough explanation, because certainly they probably were not able to swim across the ocean. The third support, rock evidence. Mountain ranges had the same type of rock or identical mineral content on the different types of mountains. It says a prime example are the Appalachian Mountains in the eastern U.S. and the Caledonian Mountains in the British Isles. They have the same rock and mineral content. So rock evidence, the third support. Glacial scars, which is one you don't really hear a whole lot about, but glacial scars, and what it's saying is that you can see in the bottom right picture the scarring, obviously from ice from glaciers, but the glacial scars were found on different continents. Location of coal deposits is another evidence that they came up with. Coal deposits have been found in temperate and polar regions. However, coal is formed in tropical regions. So what they're saying was, maybe it formed all when it was one supercontinent, when it was warmer, and then as it split apart, it just carried those coal deposits with it, and that's why we find coal deposits throughout the different continents, no matter whether it's humid conditions, cold, freezing. Seafloor spreading was another one. In the 1960s, a scientist named Henry Hess, using a new technology, radar, he discovered that the seafloor has both trenches and mid-ocean ridges. Now, if you remember from our lessons, trenches are associated with convergent boundaries, and trenches are formed when the subduction, when the land is subducted, the oceanic floor is subducted underneath the continental crust. Mid-ocean trenches are formed, or deep ocean trenches, and then the ridges and rifts are associated with divergent boundaries. Rifts and ridges, divergent boundaries, and trenches would be associated with convergent. But Henry Hess used a radar. Mid-ocean ridge, you can see in this picture to the right, that is a divergent boundary. You see the red arrows going both ways, so diverging means going apart. That's how they're formed, but there are certain things that are associated with mid-ocean ridges and divergent boundaries. Anytime you have land coming apart underneath the ocean, you have new sea floor coming up, okay, filling in that gap where it's spreading. So seafloor spreading, new seafloor, and you have rifts and ridges that are associated with divergent boundaries. When we talk about subduction zones, when we talk about converging, when you have continental crust converging with oceanic crust, that means converge, move together, it forms trenches, and that thermal energy or thermal heat that it creates as the land is being subducted ends up forming volcanoes. And this is an explanation of how a trench is formed. And this is a picture of the subduction zone as the land is being subducted underneath. So oceanic crust being subducted or going under the continental crust. And you can see how it would form that ocean trench. And they're deep ocean trenches. Evidence for seafloor spreading. In 1968, scientists aboard the research ship, the Glomar Challenger, began gathering information about the rocks on the seafloor, and scientists found that the youngest rocks are located at the mid-ocean ridge. So when we talk about where to find the youngest rock, if you go to the mid-ocean ridge where the divergent boundary is, closest to that mid-ocean ridge, closest to, let me see if I can get back to the picture, closest to the mid-ocean ridge right here would be your youngest rock. And then as the further away you go from that mid-ocean ridge, you have your oldest. So if you wanted to study the youngest rock under the ocean, or the youngest basalt under the ocean, basalt is what is mostly on the ocean floor, you would go closest to the ridge for your youngest material, and then far away from the ridge to find your oldest material. How does seafloor spreading move the continents? The magma which pushes up at the mid-ocean ridge, it provides the new land pushing up the plates, and the subduction zones gobble up the land on the other side of the plates. So there is constant movement going on under our feet, and we don't even really notice it or realize it unless you're in one of those areas that have lots of earthquakes, volcanoes, tsunamis. Plate tectonic theory, the Earth's crust and part of the upper mantle are broken into sections called plates, which move on a plastic-like layer of the mantle. Now, earthquakes, mountains, and volcanoes, all of those things, and we've already talked about this, earthquakes, mountains, volcanoes are those natural things that occur that result from the plate movements, that result from those convection currents underneath the earth that cause the movement of earthquakes, and then the magma to rise up into volcanoes, and the mountains, the folded mountains being pushed. So your convergent boundaries, your divergent boundaries, and your transform boundaries. this image is very important because it is those plate boundaries that we have, and we said around the plate boundaries is where most of our tsunamis, earthquakes, volcanoes occur. And if you take a look, you can see this is actually where the plates are divided up. So where the red lines are, where the red markings are, you would actually have more of your activity. So thank goodness North Carolina it's in the North American plate, but thank goodness we are in the middle, so we're not near a red line. Therefore, we don't get a lot of activity as far as your volcanoes and earthquakes. But you can see how the plates are divided up. The ring of fire is over to the left on that California coastline that goes all the way down. That's probably the most, I guess, infamous plate boundary, because you have such high activity in that area where the ring of fire is. Some reasons why the people didn't believe Alfred Wegener. They couldn't imagine how the earth could be millions of years old. How would people know that? And then they couldn't imagine a force great enough to move the continents, because when you think about the land, how heavy it would be, they just couldn't imagine what could move it. But by the 60s, evidence would prove continental drift true, and the story continues, as does all good science. So Alfred Wegener, who they thought was a little crazy to begin with, ended up being not so crazy. His theories proved to be true.